All right, in this video, we are going to look at Newton's second law of motion, and I'm on page 2 of your notes, starting at the very tippy top. So it says, if a net force acts on an object, then the object will accelerate. So Newton made 3 statements that seem kind of common sense. And so he thought about the acceleration, and he said, the acceleration is going to end up in the same direction as the net force. Like if you push a car left, it's going to accelerate left. The acceleration would also be directly proportional to the force, meaning if I push with a big force, I'm going to get a big acceleration. Small force, small acceleration. And the acceleration is inversely proportional to the mass. That means if I have a really big mass, I'm going to get a small acceleration. All 3 of those things make sense. So if you have even just a little bit of math background and know how to deal with ratio and proportions, you might think about it like this. So the acceleration is in the same direction of the net force. That means that this is a vector and this is a vector, so we could put half arrows on top of the A and on top of the F. The acceleration is directly proportional to the force. Things that are directly proportional have to be on opposite sides of the equal sign. So I know the A has to go here and the F has to go on the other side. And the acceleration is inversely proportional to the mass. So if the acceleration is here, things that are inversely proportional have to be on the same side of the equal sign. So just agreeing with these 3 common statements means you very quickly can agree with the statement F equals ma. So this is the way Newton's second law is commonly written. It's commonly written as an equation, F equals ma. In fact, this equation is a big deal. So everyone knows E equals mc squared, but F equals ma is like the second most popular equation in physics. In fact, we're going to be using this equation over and over for the next month. Okay, lots of stuff hidden in here. All right, so what are some things hidden in this equation? So one of the things hidden in here is the idea of some definitions that we need to know. So I'm going to flip here so that you can see my handout. Okay, so definitions that I wanted to look at. So let's look at some units here. If I wrote down F equals ma, and I was paying attention just to the units. So SI units, the mass would have to be in kilograms, so I'll write that down. The acceleration would have to be in meters per second squared. And so that tells me that the units for force are kilogram meter per second squareds. Kilogram meter per second squareds. And I get that from F equals ma. But a lot of times in physics, we take units that are kind of clumsy looking like this, and we instead honor a scientist. And we say, how about, instead of calling forces kilogram meter per second squareds, how about we honor Isaac Newton and call them newtons instead? So a newton is equal to a kilogram meter per second squared. We know that. And to be honest, I don't have that memorized. I just think of F equals ma. I know that force is measured in newtons. And then I just think to myself, well, then what would that be equal to? It would be equal to the mass unit times the acceleration unit. And then I know that a kilogram is a newton is a kilogram meter per second squared. We can also do the same thing in English units. So let's go over here. English or imperial units. So we know that we're supposed to measure our masses in slugs. So I'm going to write down slug. And we don't really use our acceleration unit very often, but it's feet per second squared. So in English, if we want to talk about the force that somebody pushes or pulls on somebody, it would be in slug foot per second squareds. Slug foot per second squareds. So I could say that a football player pushed on somebody with a force of 10 slug foot per second squareds. But again, that sounds kind of clumsy. So instead of doing slug foot per second squareds, we decided to instead call that a pound. Oh, the football player pushed down the other football player with a force of 10 pounds. Yes, a pound is a slug foot per second squared. So we just learned two definitions, the definition of a Newton and the definition of a pound. All right, so we can also use this whole concept to very quickly convert between mass and weight. So let's bring up the concept of weight. Weight is a special kind of force. So I'm going to write the word weight here. Weight. A special kind of force. What I mean by that is it gets, like, instead of just an F, I'm going to put a subscript, a W. So now it stands for weight. But you know what? Weight is just a special kind of F. So I'm going to take this equation, F equals ma, and I'm going to copy it down here in number 3. F equals m. I'm not going to write the a yet. All right, a student has a mass of 75 kilograms. What is his force in newtons? Well, this is the special kind of force, weight. And weight is the force of attraction between an object, like the person, and the earth. So if it's a force of attraction between an object and the earth, the acceleration, the a value, is 9.8. It's the acceleration due to gravity. And because it's the acceleration due to gravity, it's common to, instead of writing an a, we write a g to stand for 9.8. So FW equals mg. You and I might call this the weight equation. But you know what? This weight equation is the same thing as F equals ma. It's really the same equation. This is just a special kind of F, and this is a special kind of acceleration. But when I use this special equation, it makes it really easy to convert between mass and weight. So this person has a mass of 75 kilograms. G is 9.8. And then this would be their force in newtons. Well, it says, what is his force in newtons? That's the physics language. But in casual language, it's what he weighs. It's what he weighs in newtons. So if I multiply this out, we find out that this guy weighs 735 newtons. You used to have to put 75 kilograms in your calculator and use your calculator conversion menu to turn that into how many newtons. Now it's a lot easier. I don't have to go into the calculator conversion menu anymore. I take my mass, I multiply by 9.8, and I get my newtons. How much would the student weigh on the moon? So I'll use my weight equation for the moon. So that's going to be, his mass stays the same when you go to the moon, but the acceleration due to gravity is different on the moon. I think it's 1.63. It's 1.62 or 1.63, but I'm going to go with this. And he obviously weighs less, 122.25 newtons. I can also go the other way. If somebody gave me the weight in newtons, I could figure out what the mass is without going into my calculator conversion menu. A roller coaster weighs this many newtons. Find the mass of the roller coaster car. You just need to know if the roller coaster is on the earth or is the roller coaster on the moon. And I am assuming that the roller coaster is on earth. So I'll put in 9.8. And the mass of this roller coaster happens to be 800 kilograms. So again, using this special form of F equals ma, we can very easily convert between kilograms and newtons. All right, I skipped 1 and 2, so I do want to go back and pick those two up very quickly here. All right, so question 1 and 2 are what I call Y equations. So we have to use Newton's second law to help explain things. All right, two vehicles are stopped at a red light. One is a small car, the other is a large truck. When the light turns green, why does the car accelerate faster than the truck? let's make an assumption that the engine in the car and the truck are like kind of comparable. I'm sure the truck one's slightly bigger, but we'll assume that their F's are kind of the same. So in that sense, this will be the car, this will be the truck. That's the force of their engine. It's kind of the same. But the small compact car has a small m, so therefore it can have a pretty big A. It can have a big acceleration. The truck has a big M, and so he's going to have a small acceleration for their forces to be rather equal. And we know that when we stop at a red light that the cars can take off a lot faster than the truck. And the reason why is because as your mass goes up, your acceleration goes down because they're inversely proportional. So Newton's second law is that explanation. All right, the next one, a rocket fired from its launching pad picks up speed significantly as it's propelled upward. Why is this? Well, first of all, this seems to contradict Newton's first law, because Newton's first law says if you launch the rocket, it's going to keep on going at a constant speed forever. But now we're saying that it picks up speed significantly. So I'm going to do F equals ma. And what happens is when you fire the rocket, like the firing is like the force of the, I'll call it the engine, or whatever they used to fire it with. The rocket has a lot of fuel in it. And as it's being fired, it's burning up that fuel really fast. And as it burns up that fuel, the M, the mass of the rocket, starts to decrease very quickly. The rocket gets lighter and lighter because there's less fuel, and therefore it will start accelerating even faster. So it's not like it's violating Newton's first law. It just means that Newton's second law is coming into play. It technically staying at the same speed, but it in real life is picking up speed because the mass is decreasing. If the mass had stayed the same, then it would go at a constant velocity as in Newton's first law. But because the mass is decreasing, the acceleration does increase. All right, the last thing is a little dot here that kind of got lost in the way that said Newton's second law can also be used with the kinematics acceleration equations. And that's number 6 down here at the bottom. So before we do number 6 at the bottom, I'm going to bop back to my PowerPoint here, if I can get there quickly. Okay, so we are going to do a problem that is about something called foamcrete. So let's just read this. It says foamcrete is a substance designed to stop an airplane that has run off the end of a runway without causing injury to passengers. It is solid enough to support a car, but crumbles under the weight of a large airplane. And then by crumbling, it slows the plane to a safe stop. So for example, suppose we have a 747 jetliner with a mass of whatever and an initial speed of whatever, and it's slowed to a stop in a distance of 122. With what force does the foamcrete slow the plane? Okay, so quite simply, I'm supposed to be solving for a force, and you and I only know one equation that's got force in it, and that's F equals ma. So I'm going to write that down. All right, but let's read the problem and write down what we know. Okay, so the jetliner has a mass of 1.75 times 10 to the 5th kilograms. An initial speed, V initial, is 26.8 meters per second. It is slowed to a stop, so the final velocity is 0, in a distance of 122 meters. All right, with what force does the foamcrete slow the plane? So we know the mass. It's 1.75 times 10 to the 5th, but we don't know the A. So I can go over here And if we want, we could put an A in our list, and we could use the acceleration equations to figure out what A equals. For example, we could use the third acceleration equation that looks like this. So the final velocity is 0. The initial velocity is 26.8 squared. This is a 2. We're solving for A, and this is 122. So we're going to move this to the other side, and when I move it to the other side, it's going to turn negative. Did I do that someplace? I did not. All right, so I'll do it right now. 26.8 squared. That is a negative 718.24. Let me make sure that's right. Yep. Equals 2 times 122 will be, oh gosh, 244A. All right, so we're going to take that, we're going to divide by 244, and I get 2.94. But it's negative 2.94. All right, what it means when you get a negative acceleration is that it's slowing down, and that makes sense. That's what we want the foam crate to do, is to slow down the plane. So if I put the negative in here and I get a negative force answer, it just tells me that it's a slowing down force. And a slowing down force could be like friction. Some people don't put the negative in. They say like, oh, force can't be negative. And they just say that the answer is, you know, whatever, but you know it's a slowing down force. All right, so I'm going to take that answer, we're going to multiply it by 1.75 to the 5th power, and we get 51, 51, 31. 31.1 newtons. Technically negative, meaning that the foamcrete is slowing down the plane with that many newtons. All right, just a tidbit of what we'll be doing with Newton's second law, okay?